Hey everybody, this is Larry. This is me going Q4 of the weekly contest 456, maximize spanning tree stability with upgrades. Hit the like button, subscribe button, join me in Discord, let me know what you think about this one. Honestly, I feel really bad about this one because I took 10 minutes, which is actually reasonable, but I had two wrong answers, which is less reasonable. And honestly, both those wrong answers are silly mistakes, so I don't feel that. I mean, I feel badly about it because they are silly mistakes, but I feel good that algorithmically it was fine. It's just that today I just am bad at implementation, or maybe I was rushing it a little bit because I didn't really think through all the silly cases, and we'll go over that in code in the implementation part. So hit the like button, hit the subscribe button, join me on Discord, and yeah, let's take a look at this Q4. But the first thing to note is that whenever I see minimum spanning tree, I will immediately think of greedy, right? And some part of this is because honestly, even at its core, a minimum spanning tree is one of those canonical examples of a greedy problem and a greedy solution, right? I'm not going to go over minimum spanning tree or in this case, maximum spanning tree, maybe, I don't know. But in this video, because there are a lot of videos because on minimum spanning tree, because this is a fundamental intro to algorithms type class. So like it's in, I want to say it's in like probably most reasonable algorithms class. So I'm not going to go over minimum spanning tree. But the idea is that, because it is greedy, and in fact, because it is greedy in a couple of ways, there are different algorithms to even solve the generic minimum spanning tree one, right? That said, this is not the minimum spanning tree, but it is a different spanning tree, so we will go. First thing to note is that you have this must thing, which means that it is the tree that you're given already, or not a tree, but just some connected edges that are already put in. And as a result, you just have to construct them with those edges. And the other thing is, of course, you cannot upgrade these edges, so you have to keep track of that. So there's a lot of keeping track, which is not hard, but you just have to consider all the interactions, that's all. And then you have just some edges and a strength. And of course, this being, so the stability of a tree is defined as the minimum. And we want to find the maximum of the minimum. So of course, then the next kind of idea would be you just keep on adding edges that you can with the maximum thing. The thing with this is that, and this goes back to the greedy idea of the minimum spanning tree, which is that for each, and there are a couple of ways to do it. You could think about it globally in an edge kind of sense. Sometimes you want to think about it as a per node sense, because each node will quote unquote be connected for the first time with one edge, right? I mean, that's not to say that each node only has one edge. It just means that if this node is on an island yeah, I guess maybe an island, I don't know, on its own individual tree, and you connect it, you could kind of think of it as like a two subtrees, and you kind of connect them in any way, then you always want to take the minimum path, right? Or in this case, the maximum path, but the path that penalizes you the least, right? So minimum, but maximum in this problem, maybe that's a little confusing, right? But hopefully if you understand this problem, that makes sense. So you want to take the edge that's maximum that crosses the two components. That's really the general idea about minimum spanning tree or maximum spanning trees. And you always need one kind of, maybe I'll draw it out because I keep on doing this interpretive dance in front of you. But yeah, like the core idea is just that, I say node, but it actually is more than an island, right? So you have like two components, right? And they're not connected, and they're just a lot of edges. And it doesn't matter how many edges, which subnodes that they're connected to. It's just that, they connect to each other using these edges in the middle. And without loss of generality, they don't affect each other, right? Because they affect each other in the sense that you only pick one, and that's it, right? So that's why greedy works, is because it doesn't affect other matching stuff. Like let's say there are other components, and let's say it matches, maybe there are edges from, here or here. But if we're looking at And it may be that you don't consider these edges yet, but if you look at just these two components, at least for now, then yeah, one of these edges would be good. I mean, there may be that, you know, you want these and these instead, but now we're getting too complicated in terms of, you know. But in any case, what I mean by that is, and that's where the greedy part comes in, right? Yeah. And so, okay, so you're given already some edges, and of course there shouldn't be a cycle because this has to be exactly n minus 1. So every node has to be connected, and there has to be no cycles. It has to be a tree, right? So it's not just a connect components thing. It has to be a tree. Yeah. So okay, so that's the other thing. Otherwise, then now the tricky part about this is that, okay, if there's no doubling function or whatever, then we're done, right? We just have to connect the rest by using, I don't know, one of the minimum spanning tree algorithms, in this case to maximize. But honestly, the actual answer with the doubling doesn't change that much, right? Because then now you have all these edges that you know are going to be optimal via greedy. Well, it is still greedy, but it's a second different greedy subproblem of, okay, now you have given these edge, this tree, which edges do you choose to double? Well, of course, you just choose to double the smallest one, and that's it, right? That's it. You double the smallest edges so that they're bigger. There are no negative values or anything, so that doesn't change anything. So that's it, right? And then you just kind of go through a few edge cases to make sure that you handle them, and that's fine. All right, let's go over the code. With that said, this is union fine. If you watch me live, you'll see that I type it out manually. It takes like an extra, I don't know, 30 seconds. So hopefully, you know, this is pretty straightforward. Or, you know, if you don't know union fine, or let me write it down real quick. Union fine or disjoint set union. Data structure. So definitely do some Google, or maybe I guess nowadays just ask ChatGPT on how these things work, right? Because otherwise it's going to add another 20 minutes to my video at least. But yeah, let's say you have these, and this is a very key part of minimum spanning trees commonly, right? So definitely get to know them. But yeah, you have infinity, and then here SU just means sorted edges, and sorted. Because in the future, because I know that I wanted to, it's kind of leftover, but it's sorted by maximal, so that we can use greedy later. And we'll go over that. And yeah, that's why I had SG as Y. Yeah, and then we have left. This is number of edges left for a tree, right? And then best is just infinity. Best is just the min edge we're trying to maximize, right? And then we have infinity. And then now for each edge, if m is equal to 1, then we add this edge to the tree regardless, right? Yeah. But if there's a cycle, we return -1, what it sounds like. Otherwise, we connect them, we update the min edge, we decrement the number of edges left, right? Pretty straightforward, honestly, for this part. And this is also not different from minimum spanning trees. In general, I think there is a common-ish variation, which is just this, right? You have a minimum, or you have a lot of edges, you want to create a minimum spanning tree, but some edges are fixed. Well, then you just add them to the tree, and then you can only minimize the rest, and that's basically the idea. Otherwise, we add it to the sort list structure with the strength is the beginning, and we sort this in reverse so that the max of the edges could be in the front. Here's the things that we added so that we could sort them later. You'll see in a second. But yeah, for each sorted edge, if this creates a cycle, we skip, meaning that, you know, this does not give us a new edge, so we skip, right? Otherwise, we add this edge, keep track, add it to add it, the strength, right? Because the reason is so that we can double them. And then now, remember that we add this in from large to small order. So from the reverse, we reverse it so that the small is in the beginning. And then, yeah, we just doubled all the, we double up to K, right? That's the input. We can double k of them, so we double the cheapest one of them so that they become bigger numbers. And then yeah, and then if we still have an edge left, then and we return -1. I guess this could have been here before added, but either way, right? And this is where I got one wrong answer, is that I just forgot to check for it, right? So if there are any edges needed, we do not have a tree. It's not connected. So then we return -1. And then the rest just return the min of now or the new added ones, and best is the min edge from the must, you know, like the ones that are must. So then we just kind of return the min of those. I got one wrong answer because added could be can have 0 elements, so I have to add a default. Just a very silly mistake, but that's it. What's the complexity here? There's a couple of sorting, so it's gonna be n log n, right? Or is it n log n? Well, I mean, kind of. In that there are a number of edges, right? So there's n nodes, or let's say this again, right? There are v nodes and there are y edges, and this is going to be y log y in the number of edges because we sort the edges, right? A couple of times, but yeah, because we do the sorting on the edges, it's going to be y log y, right? And there's a lot of O of n stuff, so it's going to be n or O of v, if you will, for vertices. So it's going to be O of v plus y log y. And that's it. That's all I have for this one. Let me know what you think. Pretty greedy. And I think a lot of people got this because it's greedy. So yeah. And it's both greedy and a good chunk of it is in textbooks and intro to algorithm classes. So I think the only leap that you have to do is maybe there are two things maybe. One is that greedy on the doubling, so that maybe you have to figure that out. And then two is, at least for me a little bit, it's convincing myself that the doubling itself doesn't affect the global state, which apparently didn't. And I kind of submit this by YOLO as a result. But that's basically the idea behind that though. And yeah, that's all I have for this one. Let me know what you think. Thanks for watching. And you could watch me solve it live in the contest now. It's still not great. All right, let's take a look at today, the Q4. I reflexively look at the leaderboard, but again, it is cheaters, just bad habit. Anyway, all right, let's go. Q4, maximize spanning tree stability with upgrades. Okay, so you have nodes, edges, and must sub I. Okay, node strength must be included in the spanning tree. These edges cannot be upgraded. Okay, that's fine, maybe. You're given an integer k, the maximum number of upgrades you can perform. Each upgrade doubles the strength, and each upgrade can be upgraded at most once. The minimum strength score amongst all edges included in it. Minimum strength. This use of minimum and maximum confusing, that's why. The stability is, so we want to maximize the minimum edge. Okay. I mean, this still feels like greedy, honestly. And if you know anything about MST, minimum spanning tree, is that, in fact, it is like one of those things used to prove greedy, or like that has a greedy proof, like, you know, with monoids and stuff. I'm not gonna get into it. I kind of solved the problem and not for, but okay. What is M again? Or N? Man, I'm blind. I thought I saw M, but that's actually clearly an N. That's why I like uppercase. Also because I'm blind. Okay, so must, we have must. Okay. Does it have to be a tree? Okay, so it has to be a tree, just not just connectivity. What is this doubling? So we double the strength. Okay, I mean, I still don't get how this is different from a normal spanning tree in terms of just like sorting, because you always just want to take the minimum edge and double. Is that true? I'm trying to think whether there's a case in which it's non-greedy and that you doubled other stuff instead, right? like if we upgrade 2 other edges, maybe that's better than just upgrading 1 edges, right? And I don't know I don't know. My intuition is still greedy, but I cannot prove it. We want to add in, and in this particular problem, we want to add the max strength possible. So then it is going to be, okay, so it's just create a tree, and then because all the edges are independent, really, right, in a spanning tree. So create a tree, create a minimum spanning tree, and then yeah, I think so. I could be wrong, maybe. Okay, so maybe we have something like well, let's do a union find first. Is it zero index? Yep. Okay. Okay. Something like that. It doesn't really matter. But okay. So we have to add in a score thing maybe. But okay, that's fine. All right. So then now maybe we do one pass. UV strength must in edges. So then now we want to say sorted edge maybe, and then now if must is equal to 1, then we have to upgrade it, right? So union UV, but also means that if this creates a cycle, then by definition we cannot create a tree. Or if this, right, otherwise we will union it. And maybe I keep track of, I don't know if I need to, but I feel like I want to. Okay, else. Okay, so this is not a must, so then sorted edge dot append UVS, right? And then now we sort. Then now we're actually I won't reverse. So then now the biggest numbers are in the beginning. Oh no, I mean yes, but we should sort by strength. So let's actually put it in the front. Yeah. And for SUV in sorted edge, oh yeah, we want maybe best is equal to infinity. If we do add this, then we have to do best as best, right? Okay, so then now given SUV is an SE. What am I doing? Okay, so if we skip, otherwise we want to add this in a greedy way. We always want to add this anyway, so that's good. And then what? we don't update best. What we want to do is just keep track of the things. Maybe S, right? Okay, so then now I don't think left is needed, honestly, but okay. So then now this is now from big to small, so now add, we want to reverse, and then for I in range of K, if I is, I just min this. Oh yeah, they cannot be upgraded, just want to make sure. Okay, so then now 2, right, and then now we get return min of added. And maybe best from the other side. Something like that, I think. Oh, this needs to be an actual min, not an f min, because it's I want to get min over array. So 2, 3, -1, almost good. We have the 6 thing. Oh, this doesn't even make sense. Okay, now we're Gucci. Let's give a YOLO submit. Oof, I should have thought. I actually was thinking about that, but then as soon as I wrote it, I was like, oh wait, dumb. Is it default? Is either default or empty, I forget, but this is a dumb case. I mean, the case is fine, I'm dumb, but this is a dumb case for me not handling. Is this right? I wish when you have someone like this, they tell you the expected answer, but I think this is probably right, otherwise it just wouldn't make sense. Alright, let's give YOLO submit. Hopefully no more silly mistakes. Okay, I mean, this is definitely a silly, it's definitely a mistake. -1 means it's impossible. Maybe I should have checked left. Oh, because it's not. Oh, I didn't think I needed to check left for connectiveness, but yeah, if left is greater than 0, that means that we still have some left over. I'm just being really dumb. That's just such an obvious case, and that's why I have it here. But I was like, oh, maybe we don't need it, but maybe I rushed it a little bit. Yeah, I guess I rushed it a little bit. I should not have had 2 wrong answers on that one. Yeah, I mean, that is just silly. Silly. Yeah, I mean, very silly mistakes. Not great, but yeah. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye-bye.